A grinding wheel. At t equals to 0, a grinding wheel has an angular velocity of 24 radians per second. It has a constant angular acceleration of 30 radians per second square until a circuit breaker trips at t is equal to 2 seconds. From then on, it turns through 432 radians as it coasts to a stop at constant angular acceleration. Part A. Through what total angle did the wheel turn between t equals 0 and the time it stopped? Part B. At what time did it stop? Part C. What was its acceleration as it slowed down? So we know that at t is equal to 0, we have an angular speed 24.0 radians per second. The angular acceleration is 30.0 radians per second square for time between t equals 0 and t equals 2 seconds. And it is alpha prime for t greater than 2 seconds, which is one of the things that we need to find. Now, in part A of the problem, let's start with what is happening between t is equal to 0 and t is equal to 2 seconds. Well, we have the angular speed omega as a function of time is its value at t is equal to 0, omega 0, plus angular acceleration alpha times t. So we have an initial speed 24.0 radians per second, and we have a constant angular acceleration 30. So 24 plus 30t is our angular speed as a function of time. And we know that the angular speed reaches a terminal value at t is equal to 2 seconds. 24 plus 2 times 30, 60, 84 radians per second. So this is our maximum angular speed. Now, the angular speed is related to the change in the angle d theta dt, the rate of change of angle, so that a total angular displacement delta theta would correspond to the integral from t equals 0 to 2 omega of t dt. So we can calculate integral from 0 to 2, 24 plus 30t dt. This would be 24t plus 15t squared, which is to be evaluated between t equals 0 and t equals 2. So we find that the angular displacement delta theta will be 24 times 2 plus 15 times 4. When we evaluate that 0, we obtain 0, minus 0. So this will become 48 plus 60, 108 radians. Now, what is this angular displacement? It is the angular displacement that we obtain between t equals 0 and t equals 2 seconds when the circuit breaker is tripped. But the question is, through what total angle did the wheel turn between t equals 0 and the time it stopped? And we're given the information that from then on, it turns through 432 radians. So from the point in time where the circuit breaker trips until it stops, it turns through 432 radians. Therefore, the total angular displacement, delta theta total, will be 108 plus 432, which gives us 540 radians. Okay. Now, part B asks us to find the time it stopped. So, in between time t is equal to 2 seconds and t final time, what is happening? We have omega as a function of t given by its value at omega at t is equal to 2 seconds plus alpha prime times t minus 2. So we know its value at t is equal to 2 seconds is 84 radians per second. That's what we calculated in part A. So we start with 84, and as time goes by, we have alpha prime times delta t, where delta t is t minus 2 seconds. And when we evaluate omega at t is equal to t final, that is when we have 84.0 plus alpha prime t final minus 2.00, this must be equal to 0 radians per second. Why? That's when it stops. So what do we see for alpha prime? We have minus 84 divided by delta t final. So delta t final is t final minus 2.00 seconds. All right. Now we can calculate the total angular displacement delta theta between time t equals to 2 to t final. It will be the integral from 0 to t this is in between t is equal to 2 and t final, omega of t dt. So this will be integral from 2 to t final 84 plus alpha prime t minus 2 dt. So this is 84t plus alpha prime t squared over 2 minus 2 alpha prime t, which is to be evaluated between 2 and t final. So the total angular displacement between t is equal to 2 and t is equal to t final will become 84 times evaluated at t final minus evaluated at 2, t final minus 2, plus alpha prime over 2 t final square minus 4 minus 2 alpha prime t final minus 2. And what do we know the angular displacement is between t equals to 0 and the time when it stopped? It is 432 radians. So we see that we have 84 t final minus 168 plus alpha prime parentheses, we have t final minus 2. So this term alpha prime t final minus 2, t final plus 2 divided by 2, that's the first term here. And then alpha prime t final minus 2 parentheses, we have a minus 2 for the second alpha prime term. So this is to give us 432 radians. Okay, so what we obtain here is 84 times t final minus 2 is what we call delta t final. So this is 84 times delta t final plus alpha prime is minus 84 over delta t final. So we can substitute here minus 84 over delta t final times delta t final. And then we have t final plus 2 minus 4 divided by 2 parentheses. This is equal to 432. So one of the delta t finals cancel here. Now we have 84 delta t final minus 84, 4 minus 2, 2. So this is going to be a t final minus 2 over 2. So that's 84 delta t final divided by 2. This must be equal to 432 radians. So from this we can calculate delta t final. So this is going to give us 84 minus 84 over 2, 42. So we will have 42 delta t final is equal to 432. So we obtain delta t final is equal to 432 divided by 42, which is 10.29 seconds. So delta t final is t final minus 2 is 10.29 seconds. Therefore, t final is 12.3 seconds if we keep 3 significant figures in our final answer. So that's when it stops. All right, and part C asks us to find the angular acceleration it had between t equals 2 and the time it stopped. So that's alpha prime. Alpha prime we have found to be minus 84 divided by delta t final. And that would be minus 84 divided by 432 over 42 is delta t final, to be more exact. So this gives us minus 8.17 radians per second square as the angular acceleration in the time interval between t equals 2 and t equals 12.3 seconds. That is an angular deceleration because it's negative. Okay, so we have a grinding wheel whose angular acceleration is time dependent. So it is 30 radians per second square between t equals 0 and 2 seconds. And after that, it's again a constant, but it's negative actually because it's going to decelerate. We have an initial angular velocity, 24 radians per second. And we know that at t is equal to 2 seconds, when the circuit breaker trips, the angular acceleration changes and it turns through 432 radians until it stops at t final, time t final. So we want to know through what total angle the wheel has turned, at what time it stopped, and what was the acceleration that caused it to slow down. And between t is equal to 0 and 2 seconds, we have angular velocity omega 0 plus alpha t, where alpha is 30. So if we calculate integral omega t dt between 0 and 2, we find 108 radians of angular displacement plus 432 until it stops. So we obtain total 540 radians change in angle. So that's the angle through which the wheel has turned. Between t equals 2 seconds and t equals t final, we know that it has turned 432 radians. What is the angular velocity as a function of time? It is its value at t is equal to 2 seconds plus alpha prime t minus 2. When we substitute t is equal to 2 here, we obtain 0. So we obtain omega t at t equals 2 seconds. Okay, so that's how it depends on time. So here we have to be careful about this condition that our time scale starts at t is equal to 2 seconds. And then when time is t final, omega should be 0. So for that, alpha prime must be equal to minus 84 over delta t final. If we Take the integral 2 to t final of omega t dt and set it equal to 432 radians. We can obtain t final to be 12.3 seconds. Actually, we obtain delta t final, but delta t final is t final minus 2. And substituting this into alpha prime expression minus 84 over delta t final, we find our angular acceleration minus 8.17 radians per second square.